All right, everybody, good morning. Sorry I didn't get this out last night. Kind of actually wasn't feeling that great and kind of fell asleep early. So, going to get right back on track though, and let's talk really quickly about the SR latch. The SR latch is literally the first piece of, as far as memory, that we're actually going to be talking about. And the idea is that we're actually going to take basically an input, and we're actually going to cause the output of the latch to basically set or reset basically an output. And what we mean by that is that we're either going to cause the output to go high or actually have it go low. And the intention of doing that is that we're actually causing the latch to literally hold a value or latch that value until we actually tell it to change in whatever manner that we want to. And the three ones that we're actually going to be looking at are basically the SR latch, and we're going to quickly find out that it has limitations. From there, we're actually going to try to see if we can have other available latches or devices that will correct the issues of basically some of the forbidden problems that we come across with the SR latch. And then we're going to come into what we call the D latch, and from there we're going to go into what we call the JK flip-flop. But how do these things work, and how do they actually cause us to even develop building blocks of memory, essentially? Now remember, with memory, guys, that we're trying to actually hold a value in, essentially, literally, that we can go and then take that 1 or 0 and then query it and pull it back so that we can actually regain whatever we've stored, whether that's a picture, whether that's a document, things like that. But the latch, the SR latch specifically, is the absolute foundation of all memory building blocks. It's actually part of the D latch. It's actually part of the JK flip-flop as well. But we're going to quickly see what the problem is with the SR latch. Now, going back to our discussion that we had yesterday on the asynchronous versus synchronous types of systems, this is actually an asynchronous building block, meaning that it changes value whenever it just can change value at any time. We're going to see later on, when we get into flip-flops, that they are going to be synchronized in such a way that it's only going to be able to be changed when the clock cycle is actually going to be enabled in a very, very specific way, whether that's a leading edge or whether we just enable it high, in which we can change that value in between that clock cycle. So there are essentially 2 or 3, let's just say 3 main settings with the SR latch that are important. Now, it's made up of basically 2 NAND gates in which the outputs are actually fed back from basically one gate into the opposite gate. And the 2 outputs that we actually have are Q and Q bar, meaning that these 2 need to be opposite of each other. So if Q is 1, Q bar has to be low. And the interesting part about, and I think this is kind of confusing to students, is that the inputs are actually S bar and R bar, meaning that it's not necessarily inverted per se, but S bar is for set and then R bar is for reset. And the reason why they put a bar on top of it is that we actually cause a reset state to happen. When I say state, that means how we're actually causing the latch to function. So when R bar is 0, we are in a reset state. When S bar is 0, that's when we actually have a set state in which Q would actually go high, or Q bar actually would consequently go low. So if we look at the truth table for it, and once again, here's what I mean. When R is 0 and S bar is high, we're in a reset state in which Q goes to 0. Q bar would actually just be opposite. That's all that means. When S bar is 0 and then R bar is high, then we actually cause Q to go into a set state. in which Q bar would actually be the opposite of that as well. So when R goes low, R bar goes low, the output is 0 for Q. When S bar goes low, then the output goes high. But there are two other states that are actually very, very interesting to us. If either of these, S bar or R bar, actually are both high, nothing changes. Whatever the previous state that was held for these outputs will continue to be held, and they won't change. But there is a problem, a very, very bad and inherent problem that we have with the SR latch, and that's what we actually call the forbidden state. So if S bar and R bar, by basically putting a 0 into either of these gates, we actually cause essentially an action to happen within that logic. If they both go low, what we actually have happen is Q and Q bar that are supposed to be opposite of each other. When both of S bar and R bar go low, what happens is that these stay the same, and that's absolutely bad. We do not want that. We want both of these to always be opposite of each other because we may be using Q and Q bar somewhere else within our memory system. But if both of these basically break the rule of being opposite with each other, then these values become null and void. So the basic building block of memory, the SR latch, is actually has some issues and we need to fix it. Right now though, before we can go any further in talking about how we could actually utilize the SR latch in a system or even be able to fix its inherent issues, we are going to have to be able to make sure we understand how to deal with basically these states and these feedback loops. So one thing to note is that Q bar is actually utilized as an input to the top gate with S bar. Q is actually utilized as an input on the bottom gate with R bar. And the reason why I sent out that that document that has basically multiple steps through as basically homework for you guys is because it gets you used to actually stepping through these gates bit by bit by bit by bit and actually seeing how they work. Sometimes it actually takes maybe a cycle or two for these systems to actually get the proper output that we would anticipate to see. We're going to step through a couple of those together. But sometimes it takes a little bit of staring at it to see the thing kind of go through the correction. But if we actually go through the truth table and apply those conditions to whether it's the SR latch, the D latch, or even the JK flip-flop, the system will eventually correct itself into the appropriate output that we would expect to see. So be a little bit patient, and you may, as you're going through, just see some of the stuff and go, oh man, why is it not producing the output? Let it go through another iteration in your head, essentially, and it will correct itself. Let's start off with the set phase, in which we would actually expect basically for the output of Q to go high. Now, in order to have it in a set phase, I'm going to basically set up the prior state, meaning that what was the state before that was actually holding in memory. And I'm going to say that Q current was 0, and then Q bar was actually 1. And so what we should do in a set phase is cause Q current to turn into, for Q next, Q should go high, in which we actually have that set phase where Q is high and then Q bar goes low. So working with the feedback loop is kind of weird. You guys will be able to do it throughout, stepping through these each. But let's take a look and see if we actually have some understanding of how this should work. So if the Q current and Q bar current are actually opposite of each other, 0 is actually going to be utilized as the input to the NAND gate at the bottom. And then 1 will be utilized at the top here. So if S bar goes to 0 and R bar is 1, then that should actually cause essentially a set phase. And so we know that when we take 1 and 0 and we NAND it, then what should happen is actually Q actually becomes 1. And if that's the case, then we actually can go through, cross out the 0 right here, and put a 1, in which 1 and 1 NANDed with each other actually causes that output to go to 0. And so now we actually have 0, and then S bar being 0 as well. 0 and 0 NANDed together holds the value of Q as being 1. And as long as that stays 1, then 1 and 1 NANDed together causes Q bar to be held at 0. So essentially, by that couple of iterations right there, we have sure enough held Q next actually to be 1, and then Q bar next to actually be 0. So we always kind of have the current, and then we have the next value in which we expect to see those latch to. So let's talk about the reset state. Now the reset state means that we would basically have, it doesn't matter if Q current is 0 or it's 1, we're basically going to hold that as basically being 0. So reset. Alright, there we go. Reset. And so now we're going to actually have a state, and to prove out how this works, we're going to have Q current as 1 and Q bar current as 0. So I'm going to erase these, and actually we're going to cause a reset state to actually happen. So for a reset state to happen, that means that S bar has to be equal to 1, and then R bar actually would have to be 0. So let's see what happens when we actually cause a reset state. Okay, so here we would actually have 1 fed back into the NAND gate down at the bottom, and then we actually would have 0 at the top. Well, what happens here is that we got 1 and 0, that becomes NANDed with each other. So if 1 and 0 is NANDed, then that causes the next state for Q bar down here to become 1. Now, that means that the new value of this 0 at the top changes. That's gone. So now we have a 1 that's actually been NANDed with 1 at the very, very top. And what does that do when we get 1 and 1 NANDed together? That causes basically that 1 that was on the previous output to go to 0. And sure enough, Q next goes to 0, and that 0 would actually be fed back down and NANDed with R bar, which is 0 as well, and that holds consistently Q bar to be equal to 1. And so these two values here actually hold until we actually put it into another set or reset phase. Now, what I'm going to allow you guys to do is to investigate on your own without me saying it. We will talk about it on Wednesday. Is essentially the no change phase and then the forbidden phase, because I want you guys to see what happens there, because those two states are actually kind of weird. But what we're going to find is that in no change, basically we would hold the prior value, or we would hold the values of Q current, and then in the forbidden stage you would actually find that Q and Q bar basically equal the same. We don't want that, but I want you guys to investigate that on your own. All right, I'll see you then.